So thank you for coming to the talk on using machine learning to better understand human learning. My name is Mehran Sahami, and I'm in the computer science department at Stanford University. And what I'm going to talk about is joint work with Chris Beach, who's also one of my colleagues in the computer science department. If we want to think about using machine learning to better understand human learning, there's a few things we want to think about. One of them is understanding what's the societal need. And this is something that for this audience, I don't need to spend a lot of time belaboring. But certainly we can think about how do we increase productivity in education, because there's a greater demand for education than there's opportunities right now worldwide. There's new data sets for learning. So if we think about online systems and assignments, especially in the time of the pandemic where more systems have had to move online, we can think of the fact that new data sets are being generated, and this creates new opportunities to do machine learning. Also, we have new machine learning methods and tools, custom algorithms we can build to think about how do we address issues in education. And ultimately, if we think about the challenges of education, all of these factors come together to create an immense opportunity for us to think about how we can leverage machine learning to be able to scale up higher quality feedback in human learning. So let's look at one approach that we did in our work. If we think about the autonomous support for learning, one of the things that we want to think about is how do we help individual learners to be able to learn better, to be able to get support while they're learning, but at the same time, from the analytics that we use, help find insights for teachers that can make their own teaching better and give us more insights about education in general. So to do that in this talk, what I'm going to do is start off by talking about some learning analytics, and in the broader context, then move into thinking about modeling students' learning. So we'll look at a specific task having to do with learning introductory programming and some of the algorithms that we bring to bear so that we can improve the educational process. We can think about trying to scale up, for example, feedback to new learners based on data that we can glean through machine learning and be able to scale up the entire educational process. Hopefully also giving some insights to instructors about how to make their own teaching better in the future. And then we'll look ahead to thinking about not only the implications of machine learning in K through 12 education, but also understanding how that's situated in a broader landscape of policy and issues around diversity that we also want to address. Education is a complicated and multifaceted process, and so machine learning is one important aspect of that, but we need to understand that that is embedded in a larger context that we also need to be aware of. So let's talk a little bit about learning analytics. In terms of learning analytics, we can think about using machine learning to model human learning. That's what we're trying to do in this work. And part of doing that is the opportunity to capture data during the learning process. So traditionally, if we think about many ways in which educational outcomes are evaluated, there's a process that happens and then there's a product, some sort of educational product, whether that be a program in a programming context or an essay or the solution to a math problem. And oftentimes what happens in education now is it's just that end product that's being evaluated. If we think about the fact, though, that people are interacting with some sort of online learning system, we can capture a lot more data during the process of learning, and that might potentially give us more insights about what's actually going on with learning. So if we think, for example, of computerized tutoring systems that gather a bunch of data while students are interacting with them, online learning platforms, we've seen many, for example, where students are interacting with videos or might be interacting with short embedded quizzes. But we can also think about areas where there's more richness that we can capture. So for example, in blended learning in a flipped classroom where we might have some online activities and some offline activities. Or we could even think about the process of as students are using basic software like word processors or browsers or specialized in integrated development environments for programming to be able to capture that whole process of how they're doing the work and be able to glean something from that that's more than just what is the end essay produced or the final program. And so if we think about these opportunities, there's lots of other implications here that we need to consider. There's very important privacy and security implications here. How do we keep students' data secure so it doesn't get out into the wrong hands or identify that student? certainly in terms of scores on their work, grades that are involved. There's legal protections for that. So there's a whole slew of issues we need to keep in mind there. For the purpose of this talk, because this is a AAAI Spring Symposium after all, I'm going to focus most on the technology for now. And at the end, I'll talk about some broader policy issues. But it's important to keep in mind that there's definitely other considerations having to do with privacy and security of the data that need to be taken into consideration. So let's talk a little bit about the volume of unprecedented data that's available. So at Stanford, we have a learning platform that is actually a variant of the edX platform. Code.org is an organization that has a platform for learning specific to students learning about introductory programming. Coursera and Khan Academy offer a whole slew of learning opportunities, mostly through guided videos, but other kinds of interactive instructive as well. And so if we think about this sort of instruction, the level at which we can gather data about learning is unprecedented. If we think about how we've done education for hundreds of years, what we've seen in the last 10 or 20 years around education is really a revolution with respect to the kind of data and the granularity we can get. As one example, let's look at, in the United States, K through 12 students. And if we look at the number of learners, so each one of the little figures or icons here represents 500,000 learners. If we consider a particular platform like Code.org's Hour of Code, and this is in the early days, these numbers have actually gone up, but at the time we were working with Code.org, there were almost 30 million learners on their platform who did the Hour of Code in an early iteration. Now that number is far greater. It's actually over 100 million learners. But if you think about that volume of data, not only how it's growing, but how much you can even get from an initial iteration, it's just unprecedented for what you can do. So in a partnership with Code.org in the Hour of Code, one of the things they were interested in is how do we try to scale up feedback? So as users are actually working with the system, students are trying to do some really basic programming assignments, how do we get them feedback at scale so they can make progress when they run into issues? So the approach we're going to take to that is the notion of modeling novice programming behavior. How do we want to do this and what are our goals? So our goal here is to better understand how students are learning how to program. So again, this is an introductory programming task or a series of tasks, and I'll show you what it kind of looks like in a particular stylized language. And the big insight here, or the hypothesis, is, as I talked about before, we can now gather data about the process of generating a program as students are actually adding lines or removing lines or moving them around in their code, rather than just what the final produced code is. And so our hypothesis is that a trace of the program development, when we actually see how the students are developing their program, will give us greater insight about student understanding than just the final program, which is traditionally what we get to evaluate student code or student programming assignments. So how can we leverage that information along the way as students are programming, or what I refer to as the trace for short? The basic idea here, rather than looking at just the final submitted program of the student, is to capture additional information along the way. So the natural question is, what information are we going to capture at what level of granularity that will be useful for us to understand what students are doing? And one of the easiest ways to see that is just to consider a concrete example. And this will show you both what the learning task is in Code.org, or at least a particular variant of it in terms of the introductory programming problems, and then the kinds of things students have control over. So here's the basic setup for one of the problems. We'll refer to this as the easy problem in Code.org. The idea here is it's modeled on the video game Angry Birds, although it's a little bit different. What you're actually trying to do is you have a little bird here, and you're trying to have it go through some maze or do some sequence of actions to reach the pig. And so the idea is this is a blocks-based language. And so when the code is run, there's a set of blocks that control basically what this bird is doing, whether it moves forward. And you can see that the space of places that the bird can be and the pig can be is really a discrete grid, and it just has pictures on it to make it look nice, but is really a discrete grid where we can move forward in whichever direction the bird is facing one block. We can turn left or right 90 degrees. With each command, we can potentially have a series of those. And the idea is, again, just to get the bird to the pig. And so you can see here's what a particular program would look like, right? We would move forward, we would turn left, so the bird is facing upward, move again into this spot, then turn right so the bird is facing to the east or to the right, and then move forward gets us to the pig. So this would be a correct program. Now you would think this is a very simple program. It's 5 lines or 5 blocks of code. This should be very easy and we should see very few variants actually. But in fact, when we look at the logs from code.org, we see over 10,000 potentially unique solutions where people are trying to write this code to get the solution. And some of those are partial solutions. There are bits of code that are not quite a full solution, but are what they're using to build up to get to the solution. But the number of unique submissions or solutions we actually see is far greater than one might actually expect. Here's a more complicated problem, which we're going to call the hard problem. And it actually also shows an example of using loops and conditionals. So in terms of the kinds of programming students can do as they build up, it gets very complicated in the sense that you get a fairly robust featured language in terms of being able to have conditionals, being able to have loops in addition to the basic commands. And so here what we want to do is basically get the zombie over to the sunflower. And so the basic idea is what we want to do is repeat until we get to the sunflower. That's a particular block. And basically what we want the zombie to do is to move along this path until its front becomes blocked. That's if there's a path ahead, that means its front is clear. Whenever its path is blocked, we want to basically turn to the left. So we want to do, you could think of this as sort of a simple maze tracing program. But what this will do is get our little zombie to move and then turn and move up here and then turn and then move until it gets to the sunflower. The interesting thing here is this is a more complicated program. We've seen almost 100,000 unique solutions. So even though these programs seem fairly simple, the space of complexity for what students try to do with them is actually far more complex than we might otherwise imagine. And so because we see lots of variation, that creates opportunities for learning. So what does the code.org dataset look like? We actually had about 1.2 million students in the data set who did 20 programming assignments. I'm not going to show you all the results here, but I will show you a representative on sort of one simple problem and one more complicated problem in the vein of the 2 easy and difficult problems you just saw. Turns out in this 1.2 million students, this was actually a time when former President Barack Obama actually took part in the hour of code. We don't know if his data was in our data set or not because it's anonymized, but it's just interesting to think that this was at a time when we're really trying to ramp up computer science education. So if we look at the data, the way we think about the data is each data point that we actually get is just a snapshot of a code whenever the student changes it. So whenever they add a command or remove a command or change one of the parameters, say if they're turning left or right within a command, that's a change to the code that creates a new snapshot for us. And every time that snapshot is, we basically get one of those new snapshots, we save it and get a trace of what the student's doing as just a series of snapshots. So there's lots of other things we could have done. If we had an IDE, we could do it by each line of code added. We could actually do it at a character by character level as they were typing. Or sometimes what we've done in other contexts is every time a student saves their code or runs their code, that's when we take a snapshot of it. So there could actually be higher granularity changes between snapshots. But here we're actually getting it any time a code change is made. So what that means is for one given student, what we get is a series of snapshots over time. So each one has a timestamp, so we can also see how much time they spent on a particular piece of code before they modified it. And we get that entire sequence of code until they got to their solution or they abandoned the problem. And so we get that entire series for each student, and we get a series of snapshots for over 1 million students in the data set. So for every student, they have a series of snapshots. And as you can see, for different students, the length of their trace may be different because different students may take a different number of steps to actually get to the solution. Now, the interesting thing is if we think about each one of these snapshots as representing some state in a state diagram, what we could actually do is think about, well, for different states that a student could be in, how would some teacher tell us that they should move toward a solution? So what sort of advice would the teacher give them to modify their code one step to move toward the solution? So if we think about all of these circles or nodes representing unique solutions, some of which may be solutions to the problem, what we could think of is the notion of a teacher policy. And the idea of the teacher policy is if a student wants to ask a teacher for a hint as to how to make progress in their code, what the teacher would do is the teacher wouldn't just give them the solution. That's an easy way to get the student to the solution, but it's not going to involve a lot of learning. What the teacher would often do is help guide the student toward taking the next step that leads to a path, potentially the shortest path from where the student is now in their code through some series of steps to get to the solution. But if we think about that notion of a teacher policy being for every node, in some sense, what is the hint or advice that a teacher would give to a student to try to direct them to another node, then that teacher policy is something we might want to try to learn using machine learning techniques. And so we get lots of data from lots of students. So for student number one, we might see that they take this series of steps to get to the solution. So this is their starting code and then how they sort of modify it until they get to the solution. For a different student, they might take an entirely different path, and still some other student might take a different path, and we have these paths for over 1 million students. So we now have a data set among all these paths. We can begin to think about, from those different paths, could we learn from the amalgam of them some sort of teacher policy? And so what I'm going to show you now is a little animation that Chris Peach put together that shows you basically a particular snapshot of just a subset of the graph of the nodes that students can be in, the partial solutions, and how groups of students move through this graph. And the basic idea here is that each of these little dots represents a node through the graph. The arcs represent what are some of the more common pathways that are taken. There are some pathways that aren't represented here by an arc that a student could still potentially take. They're just not very common. And the size of the circle represents the number of students that are in a given node at any particular time. And this node down here is actually the solution state. And so we're going to see how students progress from an initial state, which is they don't have any code, into the solution state. So here's the animation. You can see the different groups of students are moving toward different nodes. And every time they reach a node, the group of students separates because different students then modify their code in different ways. And so the number of students that moves into a particular node will be different, and we'll actually see different groups moving at different rates. And you can see that first set of students just got to the solution. So they turn green when they've actually reached the solution state and solved the problem. But you can see over multiple time steps, there are some students that are actually moving further away from the goal. They're not all making progress. You can see a large amount of fragmentation as students are trying lots of different potential solutions across the sample space. So even for an easy problem, students don't just make simple progression as we would think. With a large diversity of students, we also see a very large diversity in the different sorts of approaches they take and how they might potentially try to solve this problem. And so you can see over time, more and more students are actually getting to the solution. And so the number of students that remain is actually getting smaller and more fragmented. But there are still some students that are very far away from the solution. And there are still some students that on each time step are actually moving further away from the solution rather than making continuous progress. So one of the things that might come up is we might think, what's an approach to solving this problem? So let's take a particular example of a snapshot of students' code and where they might be. So here's the easy problem again. Here's a code that a student might actually try to run to see what happens. And if we just trace this through, we can see that this code's not going to solve the problem. It's going to generate an error. What the student's going to do is move forward and then try to move forward again, which is going to move the bird into this block, and it's going to generate an error. And so we might say, okay, what are some ways if we were to modify one line of code, either an insertion, a deletion, or a modification of an existing line, what are some other common possibilities we see students go to in terms of different states when they are starting with this code? Not that they actually started with this code, they started with blank code, but at some point they generated this code. What is the next state they're likely to go into? So here's a few possibilities. One is to actually remove one of the move forwards, which is actually a step toward a more correct solution. It's still not a completely correct solution, but it would move the bird forward and turn it left so it's facing upward. That's kind of on the path you can sort of see toward a correct solution. Another possibility is a student just changes the turning left to turning right. And another possibility is just to add another move forward line. And the thing we could take a look at is what is actually the frequency of these different solutions. And what we actually find, sometimes you might think the wisdom of the crowds, we should just take the solution that most students move into in the next state. In fact, that in many cases doesn't actually give you the right answer. You can see that this case, which is telling the turn left to turn right, which doesn't actually fix the bug or move the student closer to the solution, is actually much more common than the step that actually helps move the student toward the solution. So just thinking about wisdom of the crowds, what is the most common next state, doesn't actually really get us very good progress. And the insight here is that students that are confused, that might have gotten to this state to begin with, aren't actually in the best position to select what's the next best state to go to. So if you just take the wisdom of the crowd, of a crowd that might be unwise because they're struggling, it's not necessarily going to lead to the direction you want. The way we want to think about this is if the student's at a particular state, what we want to do, if we think about just some average student drawn from the class, we want to try to move them toward the solution state. So here's the solution state. And we want to think about what is the path to move them through the solution state. So that moves through a number of intermediate steps if we want them to move along that path from where they're at to the solution. But in order for them to move along that path, they have to move through a sequence of other states. And so if we want to give them a hint, the hint that we want to give them is the hint that moves them to the next best state that's on a path to the solution. And the question is, how do we pick? Because there might be multiple paths to the solution. How do we pick an appropriate path and then to give a hint that might help move the student from the state they're in to the next state on that path? And the algorithm we have, we call it the Poisson common path. And you'll see why it's called Poisson in just a second. It has to do with the Poisson probability distribution. But the idea is if we want to predict some next partial solution, some next state that the student should go into, and then we can generate a hint that might move the student toward that solution. The way we do this is we say from the state that the student is in, what are all the paths that lead to a solution? So Z of S is the set of all paths that lead to a solution from where the student is currently at. And so P is any individual path. What we want to do is find the path that has argmin of what we think of as the cost to getting to the solution. And the way we determine cost is that we say that for every step or partial solution on that path, for every state the student would go through on that path, we sum over all the states the cost of being in that state. And the way we generate the cost for that state is we count how many times did we see a partial solution in that particular state. And the cost of being in that state is inversely proportional to the number of times we've seen the solution. The way you can think of this in terms of relation to the Poisson distribution is the lambda here represents the mean of the Poisson distribution, which is a rate. How many times in some unit period of time do we actually see this particular event? And in this case, the event would be being in this particular state. So the way we can think about it is the amount of time spent in that state is inversely proportional to the number of times we've seen that state. And so that's the cost associated with being in that state. And then we sum the cost over the entire path of the solution, and we select the path that has least cost. Once we determine what that path is, then all we need to think about is what is the step in that path that we want to guide the student to take. That's where we're going to generate the hint from. So the idea here that's interesting is it turns out we can get insight about education from building models of what teachers do. And it turns out that when we actually look at having some people who are educators in computer science, when we show them the state that a student's in and different possibilities they can go to, and they would make a recommendation as to what is the next state the student should go to, or what is the hint they would give to try to move them into that state, we can try to measure what is the correlation between what the human teacher would do and what our algorithm actually suggests. And in that sense, we can measure accuracy of the algorithm, measure it in terms of not just how often does it get the student to the solution, because a simple program that could do that or a simple system that could do that is just to give a hint, which is to give the student the solution code. But that's not actually going to generate learning. What we think is more indicative of generating learning is how often does our algorithm match what an expert teacher would say Because if it does, then our algorithm is much more scalable than a human teacher. We could actually deploy it and get results on par if it's accurate with a human teacher, but now be able to do it with the millions of learners that are interacting with this kind of system. So that's the idea, is to not only understand how to make the prediction better, but to also get some insight about what teachers are doing, because this correlates well with what teachers are doing. It gives us insight about what an expert might actually recommend to students, which is to get them on the path to the solution rather than just giving them the solution. So if we think about the problem-solving policy in some sense that we would solve, what we kind of think of is the notion of a backbone. The backbone is, in some sense, what is the most common path that leads to the solution. So if we think of state 0 here as being a solution, and some state up here, like state 25 or state 10, being the starting state where someone has no code at all, we could think of the fact that sometimes as they're moving along the path to the solution, sometimes they might do something that moves them off that path and sort of sends them off into the weeds where they're getting errors. And that's the place where we might want to generate a hint. And the idea is not to try to just jump them over to the solution, but to move them back onto the backbone path, which in some sense is the overall least cost path of getting from the starting state to the solution. So we can then measure, well, how well does this policy actually do? And so what we want to look at is the notion of our Poisson path algorithm in comparison to other methods with respect to what is its percentage accuracy at matching the teacher's prediction. So remember, we get a set of expert teachers now to make predictions, or not make predictions, but to make suggestions as to how they would guide a student. And what we want is how well our algorithm matches the teachers. And so what we find is across a wide variety of methods that we actually looked at, the Poisson path method on the easy problem actually is matching teachers about 96% of the time, and on the hard problem is actually matching about 85% of the time. So doing much better than many other algorithms, some of them including state-of-the-art methods such as doing reinforcement learning. And if we look at some things like just trying to find the shortest path to the solution, without actually thinking about how we generate all the steps along the way, that actually does much worse than thinking about the entire Poisson path, where we measure the cost of the path, not just the length of the path. And there's lots of other algorithms you can look at, but the gains are pretty substantial in terms of how well we can do. And on the hard problem, actually, the gains are much more noticeable than on the easy problem, where many methods can do reasonably well. But on the hard problem, you can see it's a much larger win. So if we think about machine learning for education, kind of in the broad sense, it is a unique opportunity in terms of the availability of large data sets and recent advances in machine learning techniques. There's even more complicated things we could do in terms of learning from these traces. And online platforms not only give us an opportunity to collect this data, but to be able to deploy our results at scale. So one of the things, for example, would be to actually take the results of the Poisson path algorithm, which we've done in some limited cases, actually deploy them on algorithms like code.org to be able to give new learners hints at scale based on what the algorithm believes is the next best step they should take. And the hints are actually based on just a little template that kind of looks at the difference between the place that they're at now in their code and the place they want to get to, and then generates a piece of natural language text that's based on a template that fills in some things that suggests, oh, maybe you want to consider looking at this instruction, or maybe what you want to do is think about how the bird can make progress in terms of getting closer to the pig, or whatever the case may be. So it's not just telling them the code, but trying to give them natural language hints based on the differential in the code. But as I mentioned at the outset of the talk, care has to be taken to understand how there is access to the data, what kind of understanding there is of openness in the development techniques, what kind of transparency we have in the process, making sure that what we're doing is fair across different populations. And that gets me into the broader point, which is we have some great challenges here, but the opportunity is even greater. But when we take that opportunity, we need to be aware of the broader educational landscape. And so this is the place where I step a little bit outside of the realm of AI and machine learning to think about what is kind of the larger problem that we're trying to solve. And that's thinking about promoting diversity in educational opportunities and the education policy that's built around all this stuff to think about how things actually get deployed and where is the need for these educational opportunities. So just to give you some statistics from code.org, they, ran some studies a few years ago and found that over 500,000 current openings exist for computing jobs in the United States. That CS majors, that this would be a very lucrative field. I don't have to tell this crowd that because you probably see a lot of CS majors, but that CS majors actually earn 40% more than the college average. And in fact, there's a huge demand for computing education. That 90% of parents want their children to be able to study CS in high school. So this provides a little bit more background for the opportunity, which is why did we go after computer science education specifically? Part of it was that we're computer science educators, so we understand that domain a little bit better. But secondly, it's a domain that has huge need for scaling up. And so the opportunity here is to try to think about not just providing more educational opportunities or using AI to help provide more support, but also thinking about doing that as a way of promoting diversity in computer science education. So thinking about the broader social issue. And so some more statistics that code.org gathered was they found that for students who try to take the AP exam or the APCS course in high school, for women, if they do that, they're 10 times more likely to major in computer science. And for Black and Latinx students, they are 7 times more likely to major in computer science. So even before they get to college, earlier experiences in computing can have a huge impact on what the diversity numbers look like further down the pipeline. But there's a problem here. Remember, 90% of parents want their children to be able to study CS in high school, at least in the United States. But only at the time the survey was taken, only 45% of high schools actually taught CS. And so there's unequal distribution to access, and part of that unequal access has to do with socioeconomic background and how well-funded schools are. So if we think about that imbalance, we can see what that imbalance looks like by looking across race and ethnicity of computer science majors in the United States. And so what we find is if we look across a number of races and ethnicities, also further subdivided by gender, what we find is when we compare these to the population overall, that Hispanics and Blacks especially are underrepresented as computer science majors. So there's not only an issue here of greater access to computing, but there's an issue here of equity as to who has access. And so if we can find ways to be able to scale up the availability of computer science education through automated methods, we can not only make CS more accessible, but hopefully also more diverse. That's really the goal. And so the opportunity there, one of the ways to now think about the policy side of this is something that code.org, along with some partners, developed a few years back that I was involved in, which was the K through 12 computer science framework. And the basic idea here is to determine what is essential knowledge for all students in computer science to try to create more pathways and more accessibility. Because we think of computing skills as critical for long-term success, and the skill gap is only going to get wider unless we can find ways of making computing available at scale and in a way that helps address the diversity issue. So the way this framework is constructed is there's a number of core concepts that get into things like computing systems, networks, and the internet, data analysis, algorithms and programming, and also social impacts of computing, and a number of cross-cutting concepts that we think of from computing, like abstraction, system relationships, privacy, communication, etc. And so we can think of core practices when we put together these concepts, and from the core of topical core and the cross-cutting concepts, which are things that cut across those topics, to think about some practices that we really want to have students engage with. And part of that, foremost is fostering an inclusive computing culture. But there's lots of other things there: collaborating around computing, recognizing and defining computational problems, being able to create computational artifacts, which is the programming part of it. That's just one piece of the much broader framework we actually need to think about. So programming is not the be-all, end-all, it's one piece. And so we need to be aware that even as we build computational tools to address that piece, to make it effective, it has to exist in a broader landscape. Now, what is a framework, and what is a framework used for? The idea behind a framework is that there's a number of concepts and practices from the framework that will inform the development of other things. One of the things that it will help to inform the development of is standards. And computer science education policy, actually education policy across the United States, is fragmented. 50 different states have 50 different standards for what their education policy should be. And so every state wants their own customized version, or districts can even have sub-customized versions, or different organizations. And so the idea behind a framework is to sort of provide the pieces, to say at a high level, here are all the pieces. You can put them together in different ways to create standards for a state or for a district. But rather than recreating all the pieces, why not take this bag of material, the framework, and construct it in a way that works for your students? And so this framework, there was a number of people involved, number of states from the United States, number of districts and organizations, including members of industry like Google, Amazon, Microsoft, and Apple, lots of organizations like the College Board and Project Lead the Way and others. And you can see there was a number of computing organizations involved, including ACM, which was where my involvement in this effort came from, Code.org, that was leading a lot of the effort, and many others like Computer Science Teachers Association and others. And if we look at, in terms of people reviewing this framework, how useful they thought it was across the board for a number of things, including advocacy, teacher training, classroom instruction, the vast majority of reviewers thought that this framework would actually be useful. Now, the question is, how does this turn into policy? And this is one of the things I would advocate for is, as computer scientists, we are researchers, but we're also in a position to be able to influence policy and see our work in a particular context having broader impact, because we can not only impact the technology, we can also impact how that technology potentially gets used by impacting policy. And so a few years back, at the time, the governor of California, Jerry Brown, signed a law to help expand computer science education. And this was supposed to be a 3-year planning process where there would be a notion of trying to create a set of standards for computer science education across all of California public schools at all grades. The idea here was to address the equity issue. Rather than just having computer science available in some schools that could afford it, could the state actually create a mandate to be able to provide instruction across all schools with sufficient support? And so Governor Brown appointed a panel of 15 people to give a set of strategic recommendations around this policy. That was my involvement as one of the people on the panel, to think about how the state of California, as just one example, many states are doing this, can develop policies and standards to actually get computer science education into all classrooms, public classrooms in the state. And so the wheels have started to roll. So just recently, in the about a year and a half ago, Gavin Newsom, the new governor of California, actually proposed $15 million to expand the broadband internet in schools, and an additional $1 million to hire a computer science coordinator as sort of a down payment for getting this process rolling out. Now, this is going to be a long-term effort. It's not something that just happens in a couple of years. And the price tag involved, to be honest, is a lot more than $16 million. There's about 6 million students in California public schools in the K-12 system. So educating those students on an ongoing basis, the price tag is going to be large, but what we're seeing is the wheels are now rolling. The recommendations of that strategic implementation panel are now being taken up, and money's actually being put behind it, so that eventually we can see a broader scale scope for computer science education, which will create more opportunities for learning, both about humans and using machine learning to be able to help improve that process. So I hope what I provided in this talk is a little bit of detail in terms of what we're doing with machine learning to try to make K-12 education, especially in computer science, more scalable, and then kind of the broader picture of what we're trying to do around policy in understanding how to make computer science education more equitable. And that always brings up the point that we always want to remember, which is when we build algorithms for machine learning or AI in general, we want to have equity in mind to be able to make sure we get the full range of participation in computing. So with that, thank you very much for your attention, and I hope you have a good rest of the symposium.